So here is the data for our illustrative example then. So what we have is the top line of the table gives you the Consumer Confidence Index for 2007. The second line of the table gives you the Consumer Confidence Index for 2009, and then the bottom row gives you the difference. The idea would be that if the difference to this is statistically different from zero and it's assuredly positive, and this gives you formal statistical systematic evidence that there is a difference between 2007 and 2009. Now, there's two reasons really why you're doing a statistical test to determine this. Firstly, you want to be as systematic as possible, and then mathematically what you're really trying to do is determine whether or not there is evidence for a discernible, measurable difference between the 2 years, even if you think, based on the sort of background financial backstory, there should be a difference. Okay, so you're trying to conduct this process as thoroughly and as systematically as possible to try and avoid as much of the guesswork as possible. Okay, so if this difference variable is positive on average, then this would give you evidence that the consumer confidence is high in 2007 and 2009, and the great financial crash has reduced. First thing you need to do in order to calculate a t-test is you need the estimated mean and the standard deviation, or the estimated standard error. So in the first basic examples you need the standard deviation. In the regression examples we'll go through much of the basic procedures are the same. So in the went through the last lecture, so the mean, what you do is you just add them up and divide by the number in the sample. So if you do this for the data on the previous slide, you end up with a mean of 72.33. The deviation, so this is the formula to use, and this is the practical calculation formula. So as I said before, sometimes actual and mathematical business formula here should be -1 on the bottom, and then this is the practical calculation version of that formula, which some other finance books don't include. The sum of xi squared is just the sum of the squared observations in the sample, and then calculate the standard deviation. The bottom line just shows you how to plug the numbers in one at a time. Don't rush this bit. I've included the there. I've seen all sorts of people rushed. Take time, and it should come out that the deviation is equal to 6.5689. So the t-statistic then is given by the estimate minus the hypothesized value of the estimated standard error. And ESE is just the shorthand used for estimated standard error. So it's if you don't remember what the ESE stands for. Now, what tends to happen is that the hypothesized value is usually 0. So if you put 0 in the top formula, you get the second formula. The t-statistic is the estimate. Usually how you sort of see this in computer software examples, okay, but in principle at least it's more general than that. But when you have the one sample t-test is something that's relatively straightforward, that the estimated standard error is just over square root of n. This is the standard deviation, n is the number of observations in the sample. Now, it gets more complicated for regression problems that we'll talk about later on in the course, but the same basic procedure holds. So the t-statistic will always be estimate minus hypothesized value over the estimated standard error, and usually just the estimate of the estimated standard error. It's harder to calculate the estimated standard error. So on this course, this will usually be calculated for you by the computer software, or if it was I would give you the estimated standard errors. But the same basic procedure and interpretation remains the same in both cases. Now I wanted to talk a little bit about p-values. So this is not difficult, but is possible to get wrong. Okay, so p-value is a measure of how strange the data is in relation to the low p-values. So low p-values look odd and would cause you to reject the null hypothesis. Round null hypothesis. And I ought to say here that my A-level teacher and lots of students make mistakes here, but it is low p-values that are significant and cause you to reject the null hypothesis. And then two-sided test, you need values in the 0.025 column, tables. Now I will go through the picture in the sessions. So the point of this is you have sort of probability that it's less than 0 or 2.5% probability that it's greater than 0. So these up to a 5% probability. The important thing is whether or not you tell me if the p 5 sort of nice and easy. It has to be like that for sort of standardised exam type questions and courseworks. Generally, project work, lesson 0.1 gives some weak evidence, inclusive evidence, so the interpretation can be more subtle on occasion. So low p-values are the thing to watch for, and I'm afraid this is a slightly strange way of setting up the problem, but the reason it's done like this is so that you can mechanize it and you can very simply mechanize and standardize a systematic approach to the analysis. So the easiest way to do this is to assume the null hypothesis that the parameter, in this case the mean difference, is equal to 0, and look for evidence against that. If you do reject the null hypothesis, if this p-value is low and the evidence is sort of such that the does not seem to be the case, then if you reject the null hypothesis, then you need to ask where the true value really is. So this isn't just passing a numerical test, there is an element of interpretation. So this is perhaps slightly artificial how it's discussed on the bottom of this slide, because this was designed for a lecture course that would be assessed by examination, but I wanted to sort of try and reinforce there's often sort of three basic points to when you conduct these tests by hand calculation. So there's the actual calculation, the referencing of the statistical tables or numerical values. That will be done automatically by a computer in the assessed coursework. Interpretation angle, which is important for this course. So it's not just a purely mathematical course. To our one sample t-test example then. So the statistic is just the estimate, the hypothesized value over the estimated standard error, and the hypothesized value is 0. Estimate would be x bar, and the estimated standard error would be s over the square root n. In this case, you can calculate the t value 1.5. Now, this is perhaps slightly artificial because again this is designed for a course that's assessed by formal examination, but it's perhaps still informative just to go through the application. So for the t-test you need a distribution with n-1 the number sample. It's the same basic procedure, but you need freedom is a number of parameters in the model, including the t-test is just a regression with p equals 1. Back to the example, so this is the value you need from tables, and the way you would express this, the absolute value of the t-statistic is 38.145, less than 2.21, and therefore p is less than 0.05. Now the way I've tried to present it is to emphasise that if this thing is bigger than the value of the tables, it is less than 0.05. So if you just go back to the other slide, the main point is that if the inequality signs point a different way, then you've done this thing correctly. If they point the same way, then you've made a mistake. And then in terms of the interpretation, so how you work it out is slightly the opposite way around to how you so the difference is significant. The mean difference of the sample is 72. This gives conclusive evidence that the consumer confidence is higher in 2007 than in 2009, i.e. the 2008 has reduced consumer confidence. So what I would say for this slightly dibbly-dobbly example is that there is a common sense interpretation that you're able to recover if you're doing this correctly. So it's sort of obvious context that you'd expect this great crash to affect the consumer confidence index, and we've got statistical evidence that this is indeed the case. See more complex examples that are not necessarily as intuitive, but for most of the examples you'll see in this course, most of the results will have an intuitive explanation if you're doing the thing correctly, and that can serve as an important cross-check that you haven't made a mistake in your calculations. And these simple steps about checking calculations I think are really important. I've known good students not do that sufficiently. So I wanted to go through then analysis in R. So just think of R or eViews or any other software package as it says there, computer, well, I meant to say calculator that's too big to fit in your pocket. So if you can use a pocket calculator, you can ultimately use R or eViews with enough practice. Two basic ways of reading data into R, which I wanted to go through. Now there's directly via the command line for relatively easy examples, a harder set or harder data set, a data set of more realistic, appreciable size than what you need the data in using the read.table command via the command line. And the easiest way to do this is to save this into a .text file in Notepad and save this to a USB stick. The reason for this is always like a robot, you need to tell it exactly what to do. So as part of that, in order to use this read.table command, you need to write down the file path. It's usually shortest and easiest, saved to a USB stick. The longer this file path is, the more likely you are to make a mistake. Currently, the shorter it is, the easier it is. So the easiest if you use a USB stick, make this as short as possible. And then the .text file has to have equal numbers of evenly spaced columns, which is an important consideration and can get a bit fiddly on occasion. So when you've downloaded R, the suggestion for this course would be to download R onto your laptop. On this, it should look a little bit like what is on the bottom of the screen there. All you'd have to do is just Google R and CRAN. So CRAN stands for the Comprehensive Archive Network. So there's a huge online community, which essentially means that it's got critical mass and momentum. So precisely because of this online community, it's well worth using R, because as you get to a higher level, this R community provides a lot of code and a lot of general programming information that you don't have to reconstruct yourself. You can just use what somebody else has done before. And because of that, you can save yourself a lot of work and do really quite advanced programming and techniques, technical mathematics and statistics relatively cheaply and easily. Now, once you've downloaded R and followed the on-screen instructions, you should just be able to click on the R icon on your desktop. To do this, you should open the command window, which is where the action happens, something like this. So it's important, I think, the session that we have in person, to make sure the screen here. Now, it's a nice and easy lecture example. You can sort of just do this straight away. You can enter the data yourself. You don't have to load this up from an external Excel or .text file. So all you would do in the command window on the screen, things here. So this is just the data, and the first set of numbers correspond to 2007. I've just called this 2007 score. So do what you like, but it's usually better if it's logically named. Try and rein in the whimsy here. And then what I've done here is 2009 score and just entered the second set of data to be associated with that. What we would then do is calculate the difference by doing this sum here. So the difference goes to the first set of numbers minus the second set of numbers, and in doing this what you see is that the first name used here, the 2007 score, has to match what you call the first data set in the top line, and then the second variable name used here, 2009 score, has to match the second set of numbers. From that, you can call these things whatever you like, although I think you have to use letters, not just numbers in the variable names. And then once you've got this variable difference, the t-test is run by just doing t.test to act as an operator on the variable difference.